Okay. Hello, everyone. Welcome to the European Non-Associative Algebra seminar. I'm pleased to introduce today's speaker, Geoffrey Janssens from Catholic University of Louvain, Belgium. He's going to talk on the Loop Hecke algebra. Please.
So thank you. Hello, everyone. So thanks to the organizers of the seminar for giving me this opportunity to speak in it about Loop Hecke algebras. So I'm a representation theorist with some background in ring theory. And today it will be about these both aspects for this Loop Hecke algebra. But before going into that, I will introduce a Loop Hecke algebra, but rather try to motivate the introduction of it. And the first part of the talk will be very much about a kind of gentle, not precise introduction to what they call Schur-Weyl duality. So as a first assumption in the talk I will do is that we all like braid groups, simply because it's one of the most basic objects one can imagine. And so I'm a representation theorist, and so I would like to make representations of this braid group. So nowadays, a classical way to do this is via solutions of the Yang-Baxter equation. So the solution of the Yang-Baxter equation, so we want to make some representation. So a representation in some vector space V, and the solution of the Yang-Baxter equation is some endomorphism of the tensor square of this vector space, satisfying some equation that I will not recall. And if you have something like this, you can make a representation of the braid group by sending the ith generator on the following tensor product. So this gives a representation of the braid group. So this is one way to make some of them, but then of course you reduce the problem a bit to making these solutions of the Yang-Baxter equation. But this is rather new, let's say. So historically, already much earlier, the German mathematician Werner Rowell, so in 1955, so Rowell, he already made a representation before that all this Yang-Baxter equation machinery was existing, and he made the following very explicit representation. So he made one with values in the Laurent polynomial rings by sending the ith generator on the following matrix. So here it's a block diagonal matrix. It is some parameter and so he constructed this representation. Okay. So this representation is not only important for historical reasons, but or because, for example, since then it was understood one could make some topological invariants like the Alexander polynomial out of it, but also because since that it has been realized that this representation is a natural way to introduce the Hecke algebra. The Hecke algebra, which in the meantime has been shown to be a very interesting algebra. And so how do you get the Hecke algebra out of it? So I should rather say the one parameter Iwahori Hecke algebra, but I would simply say Hecke algebra. And maybe also like a side remark, so for me, braid groups, as I say, I will only consider the type A braid group. But Hecke algebras exist for, of course, much more general systems. So the Hecke algebra, so this representation, first of all, you can, of course, extend it linearly to the group algebra, and then you can look a bit what is in the kernel of this representation. And if you do this, you come to the following algebra, so the quotient of the group algebra by the following quadratic relation. The following quadratic relation. So one could say, okay, what does this represent? This might look artificial, but it isn't actually, because what do we know? We know all from our beginning of our bachelor's the theorem of Cayley-Hamilton that says that a matrix satisfies its own characteristic polynomial. And this equality is actually the Cayley-Hamilton identity. So then this seems that the Cayley-Hamilton theorem holds. This is actually in the kernel of this representation of Rowell. And so it is quite natural to mod it out. And so this is the Hecke algebra. And so in particular, if you're interested in representations of the Braid group, then considering actual representations of this Hecke algebra is actually describing a subpart of the representation of the Braid group, namely those that satisfy this quadratic relation. Okay, so this Hecke algebra, that's one way of viewing this Hecke algebra, but a very other fruitful way of looking at it is by recalling that the symmetric group on n letters is a quotient of the Braid group by modding out the square of the generators. And so actually, what is this saying in terms of this Hecke algebra? It says that if you consider this Hecke algebra and you evaluate this parameter t equal to 1, then actually you simply get, if you see on this quadratic relation, if you put t equal to 1 here, you simply get the group algebra of the symmetric group. So one way of viewing the Hecke algebra is that algebra that you get by trying to get to a faithful representation from the Rowell representation. Another way is viewing it as a deformation from the group algebra of the symmetric group. And it is actually this second way that will be, for me as a representation theorist, especially interesting. So I will now discuss a little bit, very briefly, these representations of the Hecke algebra. So since I don't know the background of the people attending, I will suppose that you're not experts in Schur duality. So as I said, this Hecke algebra is a kind of deformed version of the group algebra of the symmetric group. So let's first start at the non-deformed version. So let's look at representations of the symmetric group. So one way to make a representation is by simply letting it act on n tensor copies for any vector space V, let's say of dimension D. We can let Sn act simply by permuting the n copies. Okay, whatever, one can do this, but this can become actually especially interesting if V is chosen very wisely. So, and one wise way to choose V is by taking actually it as a representation of another interesting algebra or group. And for example, one could look at the natural representation of SLD. So what do I mean with a natural representation? It is simply the dimension. So this is simply C to the power D, where SLD acts via left multiplication. So, and if you do this, so then we get actually like two actions, one from the group algebra of Sn on this tensor power, and then we get a second action by the universal enveloping of this Lie algebra SLD. And the Schur philosophy is about how that this module decomposes but as a B module. And so since I will not need the exact statement here, so let's say that the classical Schur duality, so the Schur, so in the case of these two algebras, says that, well, all the representations of the symmetric group, so in case that we have chosen D be big enough, meaning that D should be bigger than N, then you can actually recover all representations of the symmetric group out of representations of SLD with a certain condition on the weights. So a certain representation of SLD, which I will not explain now about the weights, will recover all representations of Sn. So that's what the classical Schur duality would tell us. And actually, before getting to this, what it says is that we have these two actions, so we can look their images of the group algebras in the endomorphism ring of this. And the Weyl duality actually says that these two actions commute. So it meaning that these images are each other centralizer. Okay, but so we want to say something about the Hecke algebra, and the Hecke algebra is a kind of deformed version of this group algebra. So we want now to take this classical image and look at a deformed version of it. So let's quantize this. So what would we like? Ideally, one would have, in this quantized version, one would have the quantized version of this and the quantized version of this. So one would have some vector space again in the middle, which for the moment I write with the same letter. And at the both other sides, we have parameter versions of these both associative algebras. So these indeed do exist, but I should then explain definitely what these actions are. So this is basically still the natural representation. So in the sense that the representation that I mentioned of the Lie algebra SLD, that it actually also extends to a representation of the quantized universal enveloping. And here, interestingly, this actually comes from the R matrix of the quantum universal enveloping. So this comes via the universal R matrix yeah, I should put the same parameter, sorry, which is T today. So we have the universal R matrix. So what do I mean with this? So the universal enveloping is what I call a quasi-triangular Hopf algebra. And via this, you can make representations. And so this is certain element in the tensor square. And so you can make a representation in the way that we actually saw it before. So if we look at the generators, so I now view the Hecke algebra as a quotient of the group algebra of the braid group. So I look at the image of a generator of the braid group, which I denote by Ti. One simply send it in the same way as we would do for making these representations of the braid group out of solution of the Young-Baxter equation, which was the following, so simple as I recall. So one multiplies via the left, via this R matrix. Yeah, so if we do this, this gives a representation. And if we look at these both representations, then again, the actions commute. So the images in endomorphism rings are each other centralizer. And again, we can try to decompose this as a B module. And again, under certain conditions, you will be able to recover all representations of the Hecke algebra. So that's very nice. But what is even nicer is that actually, so this second associative algebra, this quantum universal enveloping, this is called a Schur-Weyl duality partner. And actually, one can be in a partnership with quite several algebras. And actually, one can be in a Schur-Weyl duality relation with what I also call a super partner. So what do I mean with this? So there exist super Schur-Weyl partners. And so, as usual, super refers there to having to be a Z2 graded algebra. And so in the non-quantized version, so again, classical, one has, so the symmetry group actually not only acts on this natural representation of SLD, which was a d-dimensional vector space, one can also let it act on a Z2 graded vector space V0 plus V1. So this is the parts in homogeneous degree 0. This is in homogeneous degree 1. This is Z2 graded. And let's say this first vector space has dimension B, the second one has dimension L. So this, on one hand, it's quite clear that, again, the universal enveloping of this time SL DL acts on it. So recall that GL DL, these are the endomorphism. So the endomorphisms of even degree of this vector space. Of even degree of this, and for this I should then explain what would be the superstructure. Well, we simply see it as a Z-2 graded vector space in the trivial way. So it means that we put everything in degree 0. Okay, so you can consider this supersetting, and again you have the same type of Schur duality type of statement. So again you decompose this as a B module, and again you can recover the representation theory of this out of this picture. And again, one can do a quantized version. And in this quantized version, one will have, so then the Loop Hecke, the Hecke algebra that maps into this endomorphism ring of this Z2, this super vector space. And the Schur theorem in this case would say that you have an epimorphism where we can actually also describe explicitly the kernel. But this description will not be of importance for the remainder of the talks and the actual results. So as a summary, so I'm somehow giving a motivation via representation theory of the Braid group, and one then comes naturally via the Burau representation to the Hecke algebra. And while trying to understand the representation theory of the Hecke algebra, there is this tool called Schur duality, where we let it act on an adequate vector space where there is also an other quantum group acting. Now, so all this is a very classical picture, and let's now see what this Loop Hecke algebra is, and let's adapt this picture to this that setting. So let's loop it. So one way of looking at the Braid group is also as a certain motion group. So viewing it as the fundamental group of all configurations of n distinct points in R2. And one way of defining the loop Braid group is by simply looking not the configurations of n different points, but of n different circles. So n different unit circles in R3. So from a topological perspective, this is a very natural generalization of the Braid group. And again, one can find a representation. So by the way, I should say that I'm definitely not a topologist. And actually, as I'm also not an expert on the Loop Braid group. So but I simply got into contact with certain conjectures about it that I found interesting. And so if you also would like to learn about the Loop Braid group, I can only suggest you one paper, a kind of a survey, but there is also new results in, by Celeste Damiani, a journey through Loop Braid groups. And so if one reads that paper, then one also learns about the result of Brundle and Hatcher. That the Loop Braid group is connected to what is called the untwisted ring groups. and for those, a representation was known. So now we don't have only one set of generators, we have two sets of generators, sigma I and rho I. And they should both still satisfy the Braid relations. But we have also some other ones. So we have the representations like in the symmetry group. So the rho I are of square 0. And then we should have kind of mixed Braid relations. And the mixed Braid relation, so first, no, sorry, before the mixed Braid relations, so those, again, still of those that are for distance quite long enough, like in Braid groups, they should commute. And then now the mixed relations are the following. So these are really Braid relations, but where one of the generators is, but where the both set of generators appear. Okay. Okay, so this is one presentation of the Loop Braid group, and it looks quite nice because it gives the impression of having a Braid group and a symmetric group at the same time intertwined in a bit subtle way, but also not in a very strange way. So if we go back to the picture I have explained now, so I started to go to the representation theory via this Burau representation. So one could also try to introduce a Burau representation for this Loop Braid group. And this is something that Damiani, Martin, Rowell did in 2021. So Martin, Damiani, Celeste Damiani, Paul Martin, and Eric Rowell, so defined the Burau representation for the Loop Braid group. And it is explicitly given as following. So on the generator, so it takes image values in the same polynomial matrices of the polynomial rings. And for the sigma I, since that they look like a Braid group, you do like before. So you simply take actually the matrix of the Burau representation of the Braid group. And for this other rho I that has more of a flavor of the symmetric group, you take the following matrix. Yeah, you take the following matrix, and this will be again a representation. Okay, that's good. With the Burau representation, we could try to now introduce in the same way as we did before this Hecke algebra. I mean, to introduce Hecke algebra as saying, well, this representation has a certain kernel, a kernel coming from the Cayley-Hamilton identities. And that's exactly what they did. So the Loop Braid group, Loop Hecke algebra, is the quotient of this Loop Braid group modulo certain quadratic relations coming from satisfying the characteristic polynomial of the images. And in this case, these quadratic relations take the following form. So the quadratic relations express the eigenvalues and so they live in the kernel of this representation. Okay, so this is a Loop Hecke algebra, and it is definitely a very natural object because, yeah, we started with adapting topologically in a very natural way the Braid group to this circle setting, and we made basically the same representation, and we looked with the same motivation of elements in the kernel, and then we come to an algebra. So then now can start to, one can of course wonder, yeah, is this algebra also as interesting as a Hecke algebra? So for example, does it has interesting bases? What is its dimension? And so on. And so as a first remark, I would like to make is that one should be really careful with this loop Hecke algebra. Although it is all very natural, there is a lot of quite intriguing things happening. So, for instance, the symmetry group does indeed map onto a subalgebra, onto this subalgebra generated by the row I, but the loop Hecke algebra also contains this subalgebra generated by the sigma I, and on this, the Hecke algebra, the classical Hecke algebra acts is epimorph on it, but in general, both have a kernel. And this kernel is actually quite big. And the message is that these mixed quadratic relations hide many, many other very non-trivial relations. And so that one thing that Damiani, Martin, and Rowell proved, Damiani, Martin, Rowell, was that, first of all, this algebra, loop Hecke algebra, is finite dimensional. For this, they used a clever trick. And then they actually made a conjecture about its dimension. So what I said is that the dimension of the loop Hecke algebra should not depend on the parameter t, on the value of the parameter t, and it should always be equal to this, or almost always. So if t is not equal to plus or minus 1. And for the rest, they also made actually a second conjecture that I will formulate more precisely afterwards about the dimension of the corners. So if you take the loop Hecke algebra and you multiply it with a family of orthogonal idempotents adding up to 1, then you can try to understand these pieces, and they also made a conjecture about the dimension of these pieces. But the most intriguing is really this first conjecture, that this dimension should be independent of almost all parameters of t. But so in particular, they could not give a basis and so on. And so the work that I want to speak about, which I forgot to mention at the beginning, but so the work that I will now start to present is joint work with Abela Caban, Leo Schjelstraat, and Pedro Vaz. And the aim of our work is to answer both conjectures. And the first one will be answered in two ways. A first way by producing an explicit basis, and a second one is via Schur-Weyl duality. Okay. So let's first look at this Schur-Weyl duality, but in the case of the loop Hecke algebra. Okay, so let's have a very, very naive look to this binomial coefficient that I conjecture to be the dimension. So one at the stage where one is still quite lost and doesn't know where to go to, one starts to rewrite dimensions in the hope to see something else that you know. So one way to rewrite it is to note that you can also rewrite these binomial coefficients, well, in a trivial way. Sorry, I have technical issues. Okay. You can rewrite it in the technical way as the following. So this fraction times another binomial coefficient. Okay, whatever. And this fraction here is approximately 2. So one should have that the dimension is 2 times this binomial coefficient. Now, if you're into numbers sequences, or if you're into knowing dimensions of algebras, of diagrammatic algebras, then this number rings a bell. So this number is the dimension of what I call the super-temporally Loop algebra. So I will not define it because I will not need it, but once that this bell comes in, and if one is in a mood of doing Schur duality, then one reminds that the super-temporally Loop do appear in a Schur duality theorem, and I forgot who proved this for the first time. Maybe it's Sartori, I forgot, but for sure it is written in his PhD thesis. So he proved that the endomorphism ring of the quantum universal enveloping of GL11 for a certain two-dimensional, some two-dimensional representation is isomorph to this super-temporally Loop algebra that I just mentioned but didn't define. So if one thinks of this, then somehow one could say, okay, so one should get an algebra that is twice as big as this, and this is an endomorphism ring for this. So we should make this a bit bigger. So one could naively start to look at what happens if I take more endomorphism rings. So I see in the chat there is a question about what is a super dimension of V. So here I'm not speaking about super dimensions. So the super-temporally Loop algebra is called like this, but I really speak simply as a dimension of the algebra. And the vector space V is not actually a super vector space. So this, okay. So one could then try to get more endomorphisms by making the algebra that acts on the vector space smaller. So one could look at the quantum universal enveloping of the positive part of GL11. So GL11, so I defined it before. Sorry, I answered a bit in a confusing way. So that the V is a super vector space. And so the two-dimensional, when I say two-dimensional, I mean the total dimension. So the dimension of both the even and the odd part. Yeah. So the dimension as a not graded vector space. So if you take here, actually the positive part of GL11, so GL11 is a sub-Lie algebra of SL2, but where the difference between SL2 and GL11 is that the square of this typical generators, upper triangle and lower triangular generator E and F is 0. So one could maybe wonder how big this endomorphism ring is. And so let's say our first main theorem, so with Lacaban, Schjelstrater, and Vaz, is that it gives exactly the Schur duality partner of the Loop Hecke algebra. So there exists some isomorphism of the Loop Hecke algebra to this ring that I just wrote. So there exists some isomorphism, and this representation we constructed very explicitly. And so the second part of the dimension and somehow answers their conjecture is that the dimension of this endomorphism ring is exactly the one that you would like to. Okay. So this is quite nice because then we get somehow the dimension out of a theorem of a Schur type theorem. And I would like to make several remarks about this. And then I will say some elements about the proof, and then I will go further into the study of this Loop Hecke algebra and its basis. So a first remark is that this is really a GL11 phenomena. So if suppose here would have been written not GL11 but SL2, then actually this endomorphism ring, if we would take only the positive part of SL2, would not increase. So it is really something that happens for GL11. So that's quite fun. And another remark is that this, and I will say a bit more about this, is that this right-hand side, this algebra is not semi-simple. So in particular, the Loop Hecke algebra is not semi-simple. So that's already one big difference with the classical case of the Hecke algebra, but still the algebra will turn out to still be of finite representation. Okay, so let me say, okay, maybe about the proof of this, I would say of this isomorphism. So what can I say about it? So there is somehow one interesting idea. So in the first phase, we need to make a generating set. So like often in Schur type setting, so we make a generating set. And making the generating set is, I will mention some minutes afterwards, because here is definitely something quite non-trivial happening. Another thing is about making this morphism, this representation. And so for this, we actually show that one can, we simply construct some symmetric braiding on the weight representations of UQ GL11 positive part. And with this symmetric braiding, we make in the way that I defined it before, like before if I had a solution of the Yang-Baxter equation, we could make a representation. In the same way, basically, one makes a representation of this Loop Braid group. And this representation of the Loop Braid group one obtains factorizes through the Loop Hecke algebra. And so we have a generating set, and the generating set one can count is of right size. But there is really a lot of work in this first part. The second part is quite okay. And so then to somehow finish it is that one should know the dimension of the image of the representation one should construct it, and actually show that the representation we made coincides with the representation made already by Damiani, Martin, and Rowell. And of this representation, I studied the dimension of the dimension, and putting everything together, we get this isomorphism. And counting the size of the dimension of this endomorphism ring is a bit of representation theory. So we have this tensor power. One can decompose it into simple representations, and it is actually quite nice because we are working with GL11. And so one advantage of GL11 is, in contrast to SL2, is that all irreducible representations are actually of dimension 1 or 2. And so all this is quite feasible. Okay, so maybe, okay, there is two things that I would still like to speak about. So first is about the generating sets, which turns out to be a basis. And making this was mainly about understanding that these quadratic relations that we encounter to define the Loop Hecke algebra, that they really actually imply an extremely beautiful presentation of the Loop Hecke algebra. And with a very beautiful presentation, finding the basis was no longer the biggest issue. And another aspect that I would like to speak about is now simply understanding better this Loop Hecke algebra. And with the Schur duality, this is quite feasible. So so for instance, one can obtain the Weyl-Marshall decomposition of this Loop Hecke algebra. So what does this mean for the non-ring theorists in the audience? Is that, so like with every finite dimensional algebra over a separable field, one can decompose it as a vector space into one semi-simple subalgebra, direct sum its Jacobson radical. So this is a Jacobson radical. So, and this is a decomposition really as vector spaces. And so out of this decomposition, this semi-simple algebra, we have this family of orthogonal idempotents that I mentioned already before. And they sum up to 1. And so the second conjecture that so Damiani, Martin, and Rowell formulated was about the form of the following matrix. So you look at the matrix that contains the dimension of all the corners. So one acts from the left and from the right with this idempotence on the algebra, and we count the dimensions, and this we put into a matrix. And so they had conjectured the form of this matrix. And so via this Schur-Weyl duality, working on this and using methods from representation theory of finite dimensional algebras, one can prove the following theorem. Is that this matrix has the following form. So first I look at the diagonal matrix containing the entries of the nth row of the Pascal's triangle. Then I multiply it with the following matrix. And again, I multiply with this same diagonal matrix containing the binomial coefficients, and the matrix look like this. To obtain this, we basically simply go into understanding a bit everything. So we describe first all the simple modules very explicitly. We describe the projective incomposables. We describe how this semi-simple parts, not simply we compute the dimensions, we really describe the semi-simple part, and somehow we describe the Jacobson radical. So actually it is semi-simple part, and that's quite nice. So there, this beginning idea of the supertemporal leap algebra again happens, and so the semi-simple part turns out to be all endomorphism ring that actually compute with the full quantum group. So not only those from the positive part. So this is a semi-simple part, and so by this theorem that I mentioned before, this is the supertemporal leap algebra. And that's why this dimension, if we rewrote the dimension, that we somehow saw the dimension of the supertemporal leap algebra, because it is actually a subalgebra, and it is actually the maximal semi-simple subalgebra. And we really describe these quotients, not only these corners, not only the dimensions. So, okay, all this we do via methods in representation theory. So in particular, we obtain first the X quiver, the Cartan matrix, and all these type of things. And we describe also the Morita equivalence class of this Loop Hecke algebra. Okay, so that's for the people who like a bit ring theory or representation theory. So they have a lot of nice properties. But then for those who are more into the combinatorics of the basis of the Hecke algebra, so we also now construct a basis of this Loop Hecke algebra. And so let me go back to this presentation of the Loop Hecke algebra. So the Loop Braid group, so the Loop Hecke algebra is the quotient of the Loop Braid group, of the group algebra of the Loop Braid group via certain quadratic relations. As I said, the Loop Braid group has two sets of generators that both satisfy one, which is kind of looking like a copy of the Braid group, the other one looking like a copy of the symmetric group. But there is some mixed Braid relations. And above all, in the Loop Hecke algebra, we have these clearly Hamilton identities that gives these mixed quadratic relations. And they really look very innocent, but it is surprising how many relations these imply between the rows and the sigmas. And so that's, let's say, the second main theorem is that if you change the generating set, and there we will use something about the value of the parameter t, one get a very symmetric relation. Yes, so we want first to change this set of generators, sigma I and rho I. And if t is not equal to 1, and that's okay because there are conjectures about the uniformity of the description of the Loop Hecke algebra was for t not equal to plus or minus 1. If you change it to the generators that I define ui as being the difference of sigma I and rho I minus t times rather divided by 1 minus t. And if I define di as being sigma I minus rho I, again defined by 1 minus t. So that's then again a generating set, of course, of the Loop Hecke algebra. And so the next main theorem is that in this generating set for t not equal to plus or minus 1, that it has a very beautiful presentation. So for those generators, what do we see? Those generators are actually idempotent. So it's an idempotent generated algebra. And there is a lot of zero multiplication. So for example, the items ui in this order is 0. And in the converse order for e plus 1, it's also 0. And in the other direction, so this direction is 0, the other one is not 0, but it still reduces to monomials of smaller length. So here the same, the different order reduces to words of smaller length. And also the Braid relations actually become much nicer. So here we see the Braid relation, and actually it reduces to something of length 2. So in the UI, also the Braid relation reduces to something of length 2. And this is, so first of all, this is extremely symmetric as a presentation. So there is no longer this bit strange quadratic relations where should you put the t and so on. It is very symmetric. And above all, everything reduces to words of length 2 or smaller. So this is a bit of a surprising presentation at first. And the proof of it is simply a pain. So to be honest, so finding that some of these relations do hold, we found by using magma for n very small. So if we looked at the small Loop Hecke algebras, we tried to rewrite the Braid relations there. And so we got two guesses, and then proving actually that those relations do hold is very long. It's very long and very technical. But so it holds, and with this presentation, one can actually quite readily obtain a basis. So using this, one can construct a basis of the Loop Hecke algebra. Namely, the basis consists of what we call all reduced words. So these are all words, let's say W, which are first a word in the D's times then a word in the U's, but one cannot put any word in the D's and any word in the U's. They need to satisfy the following conditions. First of all, the words in the D's and the words in the U's are what I call 3-to-1 avoiding. And secondly, so if the word D contains a DI, then UI and UI minus 1 are not contained in the word U. And so this is a certain amount of words. The quantity of the such 3 to 1 avoiding, that's one of these classical bijections with the Catalan number, so that they're in Catalan quantity. But then we have this extra condition. And so it is actually we have a quite nice argument about how to count all this. So it's somehow in the direct product of two Catalans, one should count this subclass. And so with a direct product of sets of dict paths, somehow we say which square of dict paths yields this force. So that's nice to show that they generate is quite nice. Counting is not so easy, but it's a nice argument. And then proving that they are independent, we have two proofs. So that it is generating. So via this, once we have this very beautiful presentation, the generating is easy, linear independent. We have two proofs. The first one is via the Schur duality, because we simply have a generating set of the right size, and the Schur duality says what is the dimension. So it's one way to somehow, via an ad hoc way, say, well, the generating set has to be linear independent. But we give also a proof independent of the Schur duality statement. So we also give a proof via what they call higher rewriting theory. So higher rewriting theory is somehow about a higher Gröbner basis. And there, one of the four authors, Leo Scheelstraat, is really a very big specialist into this. And he wrote a very long paper of 80 pages, which you can find on arXiv, that it is very, very readable, both for people who like diagrammatic algebras, also for people who don't know diagrammatic algebras. So I can only suggest to read this, but we recall the necessary things in our paper also. By the way, our paper is not yet on arXiv, but it is up to introduction. It is everything written, so it should appear soon. Okay, so these are some things and some corollaries, and then I will finish. Some corollaries of the presentation is two other questions that were posed about the Loop Hecke algebra. The first one is that it was not clear that the Loop Hecke algebra on n letters do embed in the Loop Hecke algebra on n+1 letters, but the description of our basis given here shows that you can canonically embed the basis of the LH1 into the LH n+1, or at least you can do all this again if t is not plus or minus 1. Another corollary is one could wonder if the Loop Hecke algebra is a Hopf algebra. So the Hecke algebra isn't, and the Loop Hecke algebra is also not. But nevertheless, Bernstein and Kazhdain prove that the Hecke algebra can be embedded in what they call the Hecke Hopf algebra. And actually, via our presentation, our new presentation of the Loop Hecke algebra has a lot of similarities with the presentation of this Hecke Hopf algebra by Bernstein and Kazhdain. And actually, it maps epimorphic in an epimorph way onto the Loop Hecke algebra. So again, all this is, this is if t is not plus or minus 1, because we need this new presentation. But the kernel of this is not a Hopf ideal. And actually, you can show that, at least for the small values, the Loop Hecke algebra is not a Hopf algebra. So I cannot prove that for all n it is not a Hopf algebra, but it's not a Hopf algebra for n at least up to 5. So it would be strange that suddenly it would become a Hopf algebra after. So the question rather becomes that does there again exist, like with the Hecke algebra, does there exist a Hopf algebra in which the Loop Hecke algebra embeds canonically? And so some questions that remain. Definitely, all this is for the most of the parameters, but it's still not clear what if t is plus or minus 1? So for sure, the algebra will become bigger, and the both cases will actually be different. But again, do we find interesting things? So as I said, does there exist this loop Hecke Hopf algebra? Do there exist a loop Hecke Hopf algebra? And a more general question connected to the first part of the talk: does there exist other interesting positive Schur-Weyl dualities? Okay, so this I will stop now for today. This is what I wanted to tell about our joint work. Thank you.
Yeah, thank you, Geoffrey, for a nice talk. Other questions? Okay, I guess there are no questions. Thanks again. And have a nice week. We see each other next Monday.
Thank you. Thank you. Bye. Bye.